In this video, we will deal with the mechanical properties of materials. The behavior of materials under mechanical loadings depend on its mechanical properties, and these are mainly determined by the bond strength between the atoms. Besides, the properties are also influenced by the internal structure of the material and by making internal structural changes, applying processes like heat treatment. These properties can be significantly improved. Each material has a characteristic stress-strain curve, and this curve contains valuable information about the mechanical behavior of the material. Well, we usually apply a uniaxial tension test to characterize the mechanical properties of the material and determine its stress-strain curve. The uniaxial tensile test is a very popular test, and in this test, a specimen is subjected to a gradually increasing uniaxial tensile force, which is not an impact force, and the test is continued until rupture occurs. During the test, the applied force versus elongation is recorded as a curve like F delta L, and this curve is determined by this test. You see here a tensile testing machine, grips where the specimens are fixed, and one grip is stationary, the other one is a moving grip. On one side we measure the load, and we can also measure the elongation by measuring the gauge length, for example, with extensometers. The stress-strain curve. In a tensile test, you have a recorded force elongation data, and this you can use to calculate the stress, which is defined by the ratio of the applied force divided by the cross-sectional area, and the strain is the ratio of the change in length divided by the initial length of the specimen. If for these calculations you use the initial cross-sectional area and the initial length, then this curve is called the engineering stress-strain curve, and it will look something like this. We know that during the test the specimen will be longer and the cross-section will become smaller. So the instantaneous S and L values are different than the initial values. So if you consider this deformation in calculating the stress and strain values, then we will obtain a different curve, which we call the true stress-strain curve. Here we take again the force divided by the instantaneous section and by the instantaneous length. Then, as you can imagine, F over 0 is always higher than F over S0, and then the true stress-strain curve is above the engineering stress-strain curve. But in engineering applications where we design for the elastic region, you see these two curves are very close to each other. You can use the engineering stress-strain curve, which is easier to calculate. But if you work at higher strains, for example in manufacturing, for example forging and rolling and such kind of high plastic deformations, you must consider the change in the length. That means you must take the true stress-strain curve. Here you have the engineering and the true stress-strain curve for a metallic material. Well, both curves start with an elastic region, and after the yield point, permanent deformation or plastic behavior begins, And to realize this plastic behavior, to have to increase the stresses, which we call strain hardening. And as you see, the separation of the two curves is due to the cross-sectional changes, especially when you have local necking at this point, while this separation becomes bigger and bigger. So what can you determine with the help of the stress-strain curve? You can determine, for example, the elastic modulus, the Poisson's ratio, which we will show later, the yield strength, the ultimate tensile strength of the material, the strain hardening exponent, the resilience, and the uniform elongation, the toughness, and the ductility. Well, these are important mechanical properties which you can determine with the help of a stress-strain curve, and we will deal with each of them one by one. The initial part of the stress-strain curve is called the elastic region. Here, the stress and strain are linearly proportional, and you can calculate the slope of this curve by delta sigma over delta epsilon and call it modulus of elasticity or Young modulus. This value is a measure for the rigidity of the material. In this region, the Hooke's law is valid, and the relation between the stress and strain is given by the Hooke's law. And during the elastic deformation, if you load your specimen and when you remove the load, then the specimen returns to its initial size and initial shape. The elastic modulus is a characteristic value for the crystal lattice. So when you have, for example, steel, all of the steels have approximately 210 gigapascals. Aluminum and its alloys have an elastic modulus of 70 gigapascals. By alloying or by other treatments like heat treatments, you cannot change the structure of the crystal lattice, so the elastic modulus cannot be changed. As you see in this graph, you have the stress-strain curve for soft steel, structural steel, machine steel, spring steel, hard steel. All of them have the same slope. That is typical for their lattice. And the only thing what changes is their strength values. For example, here, their yield strength. Another important property which you can determine by the tensile stress is the Poisson's ratio. Well, if you have uniaxial stresses applied to a specimen, the length L will increase by delta. Well, if your uniaxial forces are compression, then the length will decrease again by delta. So if the length increases, we know that this radius will also change. So we will have a smaller radius and we will have a dimensional change delta prime. So the ratio of the lateral construction to the longitudinal elongation in the elastic region is called the Poisson's ratio. So the longitudinal strain is delta over L, and the lateral strain is delta prime over R. And if you take their ratios, you will get the Poisson's ratio. If one is positive, the other one must be negative. That's why I put a minus sign in front in order to get a positive Poisson's ratio value. Well, the possible values are between 0 and 0.5, but for metals, the typical values of the Poisson's ratio is 0.3. In the elastic region, you know the Hooke's law is given like this. The relation between the shear stress and the shear strain is given again by a similar formula, and this value is called the shear modulus. And then, as you see, we have three quantities which determine the elastic behavior of a material: the elastic modulus, the shear modulus, and the Poisson's ratio. And we know that if you know two of them, the third unknown can be calculated with this relationship. For example, if you know the elastic modulus and the Poisson's ratio, you can determine the shear modulus, or for other combination, if two unknown, you can determine the third one. At the end of the elastic region, the yield strength is reached, and then the plastic or permanent deformation begins. Well, this yield point is, for some materials, for example, for low carbon steels, it's a very defined yield point. For other materials, for example, for aluminum, this yield point is not well defined. For example, you have determined where to take the yield point. For this, the stress value at which a certain amount of permanent deformation occurs is called the yield strength. Especially for metals, we take the 0.2% offset. And what does it mean? So the value of stress at which a permanent deformation of 0.2% occurs is called the yield strength of the material. Well, you don't have to take always 0.2. This is typical for metals, but if you take plastic materials or materials at high temperatures, you can take, for example, 1%, well, which is most suitable in these cases. Next, strain hardening. We know that after the yield point, after this point, the deformation, the plastic deformation starts, and the stresses to continue the deformation has to be increased. This is called the strain hardening. And this region has a shape like this, and the region of the tensile curve is tried to be expressed by this mathematical formula, and here the exponent n is called the strain hardening exponent. The higher the strain hardening exponent, the curve is steeper. The lower the strain hardening, the curve is lower. When n is 0, you will have a perfectly elastic plastic material. In the strain hardening zone, well, in this specimen, the permanent elongation is uniform. So there is no local necking, and there is the mechanism that prevents necking can be explained so that deformations will start somewhere in the specimen. In the specimen, there will be some cross-section which is slightly smaller than the other cross-sections, which are neighboring cross-section. But if the deformation in this region occurs, then the strain hardening mechanism will work, and the strength of the material will increase, and the deformation over here will stop, and the deformation continues in the neighboring sections. So if a section of the specimen deforms more than the others, so in this section the strength will increase immediately, and here the deformation will stop, and the plastic deformation continues in the neighboring sections. So we will have no local necking. After the yield point, permanent deformation begins, and if we stop somewhere and begin unloading, so a part of the elongation will be elastically recovered and the unloading will be parallel to the elastic slope of the curve. But at the end, you will end up with O prime and the permanent strain O prime will remain. When you begin reloading again, the deformation follows this line, again parallel to the elastic slope, and this time the yielding will not begin at the level A, it will begin in the point A prime at which the stress is relieved in the previous loading. As a result, in a plastically deformed material, yielding begins at a higher stress. The yield strength of a deformed material increases due to strain hardening. This is the conclusion we can get. We know that in the strain hardening region, the plastic deformation is uniform. But with increasing plastic deformation, the effect of strain hardening decreases, and at a certain point, local necking or the start of concentrated deformation begins. And this necking will continue until rupture will occur. Uniform elongation is the value under necking. This value is called the uniform elongation. Up to this point, the shape of the specimen is preserved, and after this point, we may have localized deformed areas. And this point also gives us the stress value, which we call the ultimate tensile strength of the material. Uniform elongation is an important material property, and this value is needed to determine the upper limit at which a material can be deformed uniformly. For example, by manufacturing processes like stretching, drawing, without the local necking in the material. This is the limit of your allowed deformation value. In the engineering stress strain curve, we have a maximum stress or force point at the start of necking. This is due to the necking, and if the cross-section of the specimen decreases, then the force needed to continue the deformation will drop, and we will see a maximum. This value is called the ultimate tensile strength of the material. You can obtain it in a tensile test by taking the maximum force and divided by the initial section. This is also an important mechanical property, especially which we can use for brittle materials. As mentioned, after this point, the stress will drop because we will have smaller sections. In a tensile test, the appearance of the fracture surface gives also information about the ductile or brittle behavior. So in a brittle material, there is negligible permanent deformation, but for a ductile material, you will see necking and high permanent plastic deformation. So the permanent deformation at the rupture is a good measure for the ductility. So how can you quantify? Well, the percent elongation after fracture, that is the length after fracture, initial length divided by the initial length, or the reduction of area after in the fractured region, initial cross-section minus the cross-sectional area of the fractured surface divided by the initial cross-section. These are some measures for determining the ductile or brittle behavior. It can be shown that the deformation energy spent per unit volume is the area under the stress-strain curve. For example, if you take a specimen and you load it, you spend energy up to the yield point, you will see this dark area, area number 1. This is the energy which can be stored elastically. So when you release the load, this energy can be regained. So, for example, if you design springs, the energy which is stored elastically in a spring is also depending on the material's property resilience. The area 1 is called the resilience, and for springs it is a very important mechanical property. The energy spent up to the fracture, that's this area 1 plus 2, is called the toughness. Well, high toughness materials are desired. Why? Because low toughness materials are brittle. You can cause rupture without spending too much energy. So, to increase rupture, you have to increase the area. So you must have high strength and also high ductility. For example, this material, number 1, is a high strength material, but since the area is small, it's a low toughness material. Why? The ductility is low. Well, if we look at the specimen like this, specimen's strength is low, ductility is high, but again, this does not help me to increase this area. Then these two materials have low toughness, whereas this material, which has high strength and high ductility, has high toughness. Let me repeat again. The ability of material to deform permanently is called ductility. For example, this is a ductile material. Well, this is also ductile, but this is not ductile, low ductile. So you should not confuse ductility with toughness. Ductility is the ability of a material to deform permanently. Toughness is the energy spent for a rupture. For toughness, you need, of course, ductility, but also the strength of the material is also important. Here you see some stress-strain curve for different materials. A brittle material will look like this. A plastic, which has low strength but high ductility, will like this. We have already discussed that the material in the middle is tough because the area under the curve is high. Well, these curves are typical for metallic material, but you may have also different materials. For example, rubber, you see? Well, it has an elastic region like this. It is completely different, so never expect that all materials will have the same behavior. Some materials will behave in the tensile region completely different compared with the compression region. You see a cast iron or a concrete. For example, let's take concrete. So its strength in the tensile part is very small, whereas its ultimate tensile or compression strength is much higher, maybe 10 times. Well, the same you see in the tensile curve or compression curve of cast iron. Well, these are anisotropic materials. They have different properties in different directions. For steels, we said that you cannot influence the elastic region. The elastic modulus will be around 210 gigapascals, but changing the structure or the chemical composition, you may influence the mechanical properties. Here you have a low carbon steel. Well, the ductility is higher. Here you have a high carbon steel. The ductility is lower, but the strength is much higher. Well, here you see copper. Here you see cast iron. Well, in your designs, which we will use in the strength of material course, well, you will use all of these types, and so you must be familiar with their mechanical behavior. So you can take also one material and change its structure. For example, you can take steel. A carbon steel in the annealed condition will have a stress-strain curve like this. If you quench it, if you have a martensitic structure, then the same material, the same chemical composition, but the structure is completely different. You see curve number 1 and curve number 2 are the same material with the chemical analysis, with the same chemical analysis, completely different. If you take the quenched steel and temper it, then, well, you see the stress-strain curve can be organized by making different tempering processes. Well, we all discussed sigma and epsilon. We know that we have also shear loads and shear stresses. Well, in the elastic region, we said that sigma equals E times gamma, and we also have a relationship between the shear stress and the shear strain, and this G value is the shear modulus. It can be calculated with the help of the elastic modulus and the Poisson's ratio. So you have a similar curve like sigma epsilon. Now we have tau gamma curve. This is also typical for the material. And for steel, for example, E is 200, 210, G is 75, 76. These are typical values. G is also a lattice property. Typical for it lattice, it cannot be changed by heat treatment and similar treatments. Well, in this last slide, we will discuss different stress-strain behaviors. Most metallic materials are elastic plastic. They have an elastic region, a yield strength, and a plastic region, some with strain hardening, some without strain hardening. Materials, especially brittle materials like glass, are perfectly elastic. They don't have any permanent deformation. You load it, if you unload, all the strain is recovered, and you reach, after a certain level, rupture. Some materials are perfect plastic. They don't have any elastic deformation. So you apply a force or stress, then deformation will occur. And if you release the load or the stress, nothing will recover. So the shape will still remain the same. There are some materials which we call viscoelastic. These are rate-sensitive material. Their mechanical behavior depends on the rate of straining. At higher strain rates, we have high stresses, and at lower strain rates, we will have low stresses. Okay, this is the end of this video. In this video, we have discussed the mechanical behavior of materials, and we have gone into the details of the tensile test and discussed the properties, the mechanical properties which can be determined with the help of a tensile test. Thank you for listening.